Hello students, and welcome to today's lecture, which is going to be on the oxidation of alkenes. And the oxidation of alkenes is going to essentially be the addition of a oxygen molecule to our alkene molecule, and therefore we're going to end up having a loss of charge on the carbon. This entire section can get a little bit complicated, and there's a little bit more memorization going on here. But the basic things that we need to know is that we're always going to be adding some sort of oxidizer, which is going to be some sort of chemical that's going to be useful for adding oxygens to our alkene. And then we're also going to go ahead and make sure that we have a balanced equation. And the oxidizer that we're going to be using most often is going to be potassium permanganate. And this is what potassium permanganate looks like. It ends up having this nice purple color. These crystals are actually a very deep violet color right here. And what you see here is that we have our potassium ion. And this ion doesn't really do all too much. It just kind of balances out our molecule. And then we have the manganate ion. And as you guys can see here, this manganate ion has an oxidation state of +7, okay? Which means that it has essentially given up a lot of its electrons to these oxygens here. Because it has that oxidation state of +7, this atom can end up being reduced by quite a lot, which is why it's a great oxidizer for our purposes. And when this gets reduced, it's going to make a lot of free radical oxygens. And that's the main idea, is that these free radical oxygens that come off of here are then going to be the oxygens that we're going to add to our compounds as we go forward. Okay, there are two types of reactions that we are going to go ahead and go over. One is going to be a reaction with potassium permanganate that's cold. So this will be a cold solution, and then a warm solution is going to be our second one, okay? And in a cold solution, what's going to happen is that the potassium permanganate solution, when it is added to our water, is going to go ahead and add two alcohol groups to our ethene along that double bond, or our alkene along that double bond. Okay, and it just basically attacks that double bond really quickly and effectively, and it's going to add an alcohol group to both ones. And we need to make sure that we're including the water in this particular reaction, because this is also how we get our OH groups. So let me go ahead and show you what that's going to end up looking like here. So our typical molecule that we're going to have here is going to be, our C, and it's double bonded to another C. Okay. We're adding H2O to it, and we're adding these oxygens to it, these free radical oxygens to it. And what will happen is that these free radical oxygens are going to go ahead and attack this double bond here. Okay, so these oxygens, they're really, really greedy. We already know oxygen's really greedy for electrons. So it's going to see that double bonded carbon, and it's going to be like, oh man, that's some tasty electrons. And when that happens, we're going to end up getting not a double bond. We're going to end up getting those oxygens attaching to and forming what's known as a diol. And a diol is just an alcohol that has, two alcohol groups on it, okay? And that's for if we have a cold solution. So the idea is that a cold solution doesn't have quite as much energy involved, and because there's not as much energy involved, the double bond will get attacked, but it will only get attacked once. Okay. The next one is when we have a hot solution. And a hot solution is going to be a little bit different depending upon the molecule. And the idea is that if the compound itself ends up having no R groups, then what will happen is that the double bond will end up breaking. So ideally, when we have hot potassium permanganate solution, because we have that double bond and there's a little bit of tension in that double bond can end up breaking completely for all of our alkene molecules. And the molecule that forms afterwards is going to be based off of that break. Depending upon how many R groups there are, it's going to be different. So for instance, the first type of molecule that we have is an ethene where a carbon is not attached to any R group whatsoever. And when we have a carbon that's not attached to any R group whatsoever, that's going to end up making a carbon dioxide. That's just going to go ahead and break apart, and it's going to make carbon dioxide, and that'll be that. Okay, we'll have carbon dioxide made, and then we'll have nothing. If it has a single R group, it's going to end up making first an aldehyde, and if we continue to allow it to oxidize, it's then going to go ahead and make a carboxylic acid. Okay, so if it has one R group, this is going to be a case where we're going to say that we have two major products that are formed. We're going to make an aldehyde and a carboxylic acid. And notice this is because it has one R group that's associated with it. Okay, and for both of these reactions, we're going to have to end up considering both the carbons on the side of it. So that's just something to keep in mind here, that we're going to be concerned with both carbons. Here, this carbon doesn't have anything associated with it. So in this case, we would make an aldehyde, and we would also end up making some CO2. If we allow that to sit in there after the aldehyde has been made, it's going to further oxidize to a carboxylic acid. So whenever you have a single R group, it's always going to end up making an aldehyde and a carboxylic acid. So you'll have two products that are made, two products. The next case is if it has two R groups, it's going to go ahead and oxidize to a ketone. And the ketone is because, it oxidizes that oxygen there, and then it's still connected to both of the R groups right next to it. Okay. And so this is a case where, you have to kind of memorize where it's going to go ahead and break. I think it's easier to think about this as the double bond's going to break, and it's going to add on as many oxygens as possible, because that's what's going on. We're oxidizing this compound. It's going to add on as many oxygens as possible. And it's going to do that by kicking off any of the hydrogens, and I think that's the good way of thinking about these kinds of reactions. And it'll kick off those hydrogens, but it won't necessarily be able to kick off those carbons there. So right here, what we have is an example of a typical question that we might have here, where we say that we have 2-methylbutene, and it's heated in acidified potassium manganate solution. All right. So we have a hot solution, so we know it's going to oxidize well. Draw and display the formula of the products and name them, and then write a chemical equation using the oxygen as a free radical to show the atoms involved. Okay, so we're going to go ahead and go to our sketch pad, and we have 2-methyl butene. Okay, this E should not be there. All right. So, 4 carbons. We have 1 methyl group, and we have a double bond between the two. All right. In this particular case, we should notice that we have two types of carbons. One carbon here, a second carbon here. It's going to break along this bond. Carbon 1 has two R groups. So that means that carbon 1 is going to form a ketone. Carbon 2 only has one R group, okay? Which means that it's going to go ahead and form first a carboxylic acid, a aldehyde, and then it will go ahead and form a carboxylic acid. Okay. This molecule here is propanone. This one right here is ethanoic acid. Okay. And here we have our naming for it. So we just figured out what compounds came off of this based off of our rules, and then we named them. All right. Now, the next part that it said is that we had to go ahead and write a balanced equation. All right. So this one, we would go ahead and just write out what its actual compound, what the actual compound was. All right. So we're going to go ahead and use our shorthand, where we're going to have CH3 C to this, we added our free radical oxygen. And we ended up making CH3, CH3. This has two CH groups. And this one right here. What you'll notice here is that when we end up having all of this here, if we went ahead and counted up our hydrogens, we should have 1, 2, 3, 7. Let me double check here. Oh, there we go. All right, so here we should have a total of 10 hydrogens. Let's go ahead and count our hydrogens over here. Here we have 6, 4. We have 10 hydrogens. We have the same amount of carbons, which means that we just have to balance out our oxygens here. Here we have 1, 2, 3. Therefore, we would put a 3 in front of the free radical here. All right, and that's how we have a balanced equation for this one right here. The next type of question could be this one right here, and it's saying, hey, name and draw the displayed formula of the organic product formed when propene, okay, propene is oxidized by a cold solution, okay? So this is a cold solution of potassium manganate. Okay, and this is propene. Since it's propene, we can go ahead and draw 3 carbons. Okay, it doesn't really matter where we draw the double bond. We can go ahead and draw it here. This is our original one. We're adding a cold solution, and a cold solution is going to end up making a diol. And so that would be our answer right there. All right. So the idea here is just knowing how this reaction is going to go ahead and move forward so that we can correctly identify the products that we're going to end up making. All right. This is going to go ahead and close us out for right now. And as you guys have questions, please feel free to ask while we work on the worksheet today.